So let's say I'm going to take one of these. So we have, let's say we have, oh, let's make sure we can write on the place and see the things. Okay. Let's say we have the following: f of xy equals xy minus 2x squared minus y to the fourth. But we also have that x is a function of t and r, and it's equal to t squared plus r cubed. And y is also a function of t and r, and it's equal to t to the fourth minus r squared. And so we're going to be asked to find del f del t. And I mean, I like to draw the little diagram. I find it helpful. So I'm thinking of f as a function of x and y, and then x and y are both functions of t and r. Really, you don't have to draw this stuff, right? Like if you're trying to find del f del t, you're like, well, okay, f is a function of x and y. So I know I'm going to have del f del x and del f del y. And then x and y are both functions of t and r. So I need specifically del x del t and this times del y del t. Basically, it's all the ways you can get from f to t. And then we're going to calculate CLT. Del f del x is not particularly nice. It's going to be y minus 4x. And then del x del t is going to be 2t plus, so del f del y is going to be x minus 4y cubed times del y del t is going to be 4t cubed. Now, one thing someone might ask you to do is to find del f del t and express it in terms of u, sorry, not u, of t and r. Which I think, and there was definitely someone had a homework problem like this. So at this stage, we wouldn't quite be done. And it's kind of gross, but then we would have to plug in what y and x were equal to in terms of u, in terms of t and r. So we'd say, okay, well, that's going to be t to the fourth minus r squared minus 4 times t squared plus r cubed times 2t plus, and then we would do the same thing here. We'd have x is t squared plus r cubed minus 4 times y, which is t to the fourth minus r squared cubed times 4t cubed. It's not pretty, but it's just an exercise and putting something else in something else. But yeah, it does seem interesting that his practice exam doesn't have any chain rule. I don't know if that's true false stuff. No. Yeah, that seems mildly surprising to me. Double check. It looked like problem 4 or problem 5 could be, but they're not. Yeah. So to me, that kind of says, well, we could spend more time on the chain rule. It might not be super present on your exam because there aren't any practice problems on it. It just feels like, what else? I mean, I can certainly talk about things, but.
I watched this one homework problem, I think 33 or 31, where you had to find the rectangle thing and you put the maximum value.
Sure. I think, let's see. So I have an example similar to that. Actually, this is problem 31 from section 9.6, where we want to find the volume of the largest rectangular box in the first octant. So when you see that you're in the first octant, all you should be thinking is that x, y, and z are all greater than or equal to 0. That's what it means. Oh, sorry. That's what it means to be in the first octant. Just like in 2 dimensions, if you're in the first quadrant, you're in the upper right quadrant where x and y are both positive or greater than or equal to 0. So in the first octant, 3 of its faces are on the coordinate planes. So meaning, right, there's a face on the XY plane, there's a face on the XZ plane, there's a face on the YZ plane. And then, and there's one vertex or corner on the plane X plus 2Y plus 3Z equal to 6. And not that you need to draw a picture, but it's kind of nice to draw a picture. So if we draw our coordinate axes, the idea is, well, if I draw this plane, it's pretty easy to draw. We just find the X, Y, and Z intercepts. So I'm going to get an X-intercept of 6, a Y-intercept of 3, a Z-intercept of 2. Just going to look, something like this. So here's my X-intercept at 6, Z-intercept at 2, Y-intercept at 3. Nope. Sure, close enough. So there's my plane, part of my plane anyway, right? I can't draw the whole thing. And then here's our box. Maybe it looks like this. And I've drawn it kind of not excellently because that little part there shouldn't be touching the corner under, but like the point is this corner here is on the plane. And so if I want to say the volume of my box, well, if this side is X, this side is Y, and this side is Z, the volume is X times Y times Z. And then we can solve, we can use the fact that this point here is on this plane. So we can isolate one of those variables. Now, typically, people would probably choose to isolate Z and plug it in so you have a function of X and Y. And that's fine. No, that's probably what we should do. Normally, I would, so if it were up to me, I would choose to isolate X here. And in fact, let's do it that way, just so we can see. It's going to be a little bit easier. So X is going to equal 6 minus 2Y minus 3Z. And then we're going to plug that into our volume. So the volume is now going to be a function of Y and Z, and it's going to be 6 minus 2Y minus 3Z times YZ. The only reason I would pick X here is because I don't have to divide by anything, right? If I pick Z, I have to divide by 3. It's going to be a little more effort. So I'm going to multiply this out. My function V is, let's see, 6YZ minus 2Y squared Z minus 3YZ squared. And now we're going to do the usual thing when you have a function of two variables to try and maximize it. We're going to take the partial derivative, set them equal to 0, find the critical points. And then we probably should also check to see if it's actually going to give us a maximum volume. So my partial with respect to Y is going to be 6Z minus 4YZ minus 3Z squared. It's kind of a little gross. Yeah. And then we're going to set that equal to 0. And VZ is going to be 6Y minus 2Y squared minus, what am I going to do here? Let's see, 6YZ. And the thing to notice about these particular equations is we can factor out a variable from each of them. Or from this first one, we can factor out a Z and say that Z times 6 minus 4Y minus 3Z equals 0. In the same way, here we can factor out a Y to the 6 minus 2Y minus 6Z equals 0. Okay, so here's what this gets me. To find the critical points, I'm going to set each factor equal to 0. So either Z equals 0 or 6 minus 4Y minus 3Z equals 0. And here, either Y equals 0 or 6 minus 2Y minus 6Z equals 0. So let's talk through this for a second. These don't make sense in that if I'm trying to make a box with the biggest volume, I don't want one of my dimensions to be 0. So I definitely don't want Y equal to 0 and Z equal to 0. That would be a problem. I also don't really want, because right, if Y equals 0 and Z equals 0, then X would be 6. So I'd have a box that was just like a length of 6 and no other dimensions. Similarly, I don't want y equal to 0 and that equal to 0 because I'll still have one of the dimensions being 0. So we set y equal to 0 and did this, I'd have 6 minus 3 is equal to 0, so I'd have z equal to 2. But still, that's going to be a box where one of the dimensions is 0. So what I'm really trying to say is we don't even have to think about either of these conditions. We really just need it to be this and this. Both 6 minus 4y minus 3z equals 0 and 6 minus 2y minus 6z equals 0. And then we can solve that system of equations in any way we want. What I would probably do is say they're both equal to 6. So 6 equals 4y plus 3z and 6 equals 2y plus 6z, and then set those equal to each other. There's lots of different ways to solve a system like this. I was just trying to look for the most. I saw they both had a 6. I'm like, oh, isolate the 6 and then set them equal to each other. So then that's going to give me 4y plus 3z equals 2y plus 6z. So 2y equals 3z. So y equals 3 halves z, and then plug that thing back into one of the equations. So if I plug, actually, let's just do that. Let's plug this in there and say, oh, 6 equals 3z plus 9z. So 6, plus 9z. I was doing the adding already. 3z plus 6z. So 6 equals 9z. So z equals 6 over 9. So I'm getting z equal to 2/3. And then y is going to equal 3 halves times z, which is going to give me 1. All right, so now I should really do, so this is where things kind of get a little handy. You could be like, well, that's clearly my maximum, right? There's no other point, it's got to be the maximum. But if we wanted to check, okay, do we really want to check? I don't really want to check. Okay. So to check, right, we're going to find capital D, which is going to be VYY times VZZ minus VYZ squared at our critical point, which is y equal to 1, z equal to 2/3. So let's see, VYY is going to be 0 minus 4z minus 4z, right? That's it. And VZZ is going to be 0, 0, minus 6y. And then minus VYZ is going to be, let's see, 6 minus 4y minus 6z squared. Now, I don't really have to be super like rigorous about evaluating this. I just have to see what side it is. So if I plug in 1, 2/3, I'm going to get, let's see, -4 times 1. Oh, sorry, that's my, I should be careful, right? That's my y value. That's my z value. So I'm going to get -4 times 2/3 times -6 times 1 minus 6 minus 4 times 1 minus 6 times 2/3 squared. So let's see. Get the calculator. So let's see. 4 times 6 is 24, times 2 is 48, divided by 3 is 16, minus 6 times 2/3 is 4, and 6 minus 4 is -2. So it looks like this is positive, which means what? Well, it means we don't actually know yet. Here's what I know it's not. I know it's not a saddle, right? Because you only get a saddle, right? You only get a saddle if your D value is negative. You get, if the D value is positive, then we have to check. So it's going to be a maximum if one of your second derivatives is negative. It's going to be a minimum if one of your second derivatives is positive. Because what we're thinking about there is if one of my second derivatives is positive, it's concave up. So I have a minimum. If one of them is negative, it's concave down. So all we're going to do is check either one of our second derivatives. Well, let's see. VYY was -4z. And if I plug in the point 1 comma 2/3, it's definitely going to be negative, which means we have a maximum. So we have a maximum at y equals 1, z equals 2/3. Now we're not quite done, because the question when we started said, find the volume of the largest rectangular box. We haven't even found all the dimensions yet, really. So if we wanted to find the volume, I would probably find the x value. So I'd use this equation and say, oh, x equals 6 minus 2y minus 3z. So that's going to equal 6 minus 2 times 1 minus 3 times 2/3, which is 6 minus 2 minus 2, which is 2. And then my volume would be x times y times z, which is going to be 2 times 1 times 2/3, which is 4/3. So it is important, especially in these optimization problems, to make sure you answer the question that's being asked. Most of the time, the question that's being asked is, what are the dimensions of such a thing? Or what's the point on the curve that's closest to the other thing? But sometimes they'll ask you for actually the maximized or minimized value. So they could ask, what's the volume? Or what is the distance between these 2 points that's the shortest? So just be careful when you read the question, if there is a question. Let's do one more, because there is something that I think is worth seeing. Yeah. So I want to find, so again, there's 2 ways I could phrase this next question. I'm going to phrase it as find the point on the plane x plus y minus z equal to 1 that is closest to the point 2, 1, negative 1. And this is number 23 from section 9.6, in case that's meaningful or helpful anyway. I'm going to just show you this picture that someone else has drawn, because drawing this plane is never easy for me. So here's the plane. It's got intersection points when x is 1, when y is 1, and when z is negative 1. And so there's the plane. It's kind of like coming up at us. And then here's this point over here at 2, 1. Right. I don't know about that, Grant. That looks, I don't know if that's really 2. So it's supposed to be the point 2, 1, negative 1, where you've got 2 in this direction, 1 in this direction, and 1 in that direction. So maybe it's really more like down here. But still, the point is that this point is not on that curve or on that plane, right? You could plug in those values to that equation and it wouldn't work. 2 plus 1 minus 1 doesn't equal 1. So we just need to make sure that we know that, because otherwise the answer would be 0, right? The point, or I should say the point that's the closest on the plane would be the point. So since the point's not on the plane, we're going to do some work. So to do this, we want to find, or we want to minimize the distance. I think this pen is trash. Between the point 2, 1, negative 1, and the plane x plus y minus z equal to 1. All right, well, we know how to find the distance between 2 points. So what we're going to do is we're going to say there's some point on the plane that is the closest point. We're trying to find it. Since we don't know what it is, we're going to call it a name. We're going to call that x, y, z. And so if we're trying to minimize the distance between these 2 points, well, we need to calculate it. Distance between these 2 points is going to be the square root of x squared, x minus 2 squared, plus y minus 1 squared plus z minus 1 squared. And as is often the case with these optimization problems, we're going to start off either wanting to maximize or minimize something that has 3 variables in it. And we're going to use our constraint, the fact that this point has to be on this plane, whose equation is x plus y minus z equal to 1, to isolate or remove one of the variables. In this case, since it doesn't, like, you could solve for any of them equally well, I would solve for z, because we like doing things in terms of x and y. So solving for z, I'm going to get z equal to x plus y minus 1. I just added z to the right hand side. And then I'm going to plug that in there. So I'm going to get that my distance equation is now the square root of x minus 2 squared plus y minus 1 squared plus, let's not write x plus y minus 1 plus 1. Let's just write x plus y. Right, because z plus 1 would be that. Now, here's a really, really nice thing to know. Instead of taking the derivative, the partials of this and setting it equal to 0, instead what we can do is make an observation. The minimum value, or maximum value, but specifically the minimum value in this case, of the square root of some stuff really just depends on the minimum value of the stuff in the first place. Right? If you make the inside part as small as possible, assuming that it's still it has to be positive. If you make that as small as possible, you're going to make the square root of it as small as possible. And really it's just because the square root function, right, is an increasing function. So if you make the input as far left as possible, you're going to make the output as far down as possible. It's really nice. What this means is we can instead just minimize the square of the distance. This is always true. It always works. It's something that is you can always count on working. Another way you can justify this to yourself, if you don't feel super convinced by this, is the fact that if what you're really trying to do is you're trying to take the derivative and set it equal to 0. So you're trying to find the derivative of this function of x and y and set it equal to 0 and solve that. Well, if you take the derivative of this instead, if you use the chain rule, the derivative of something squared is 2 times your something times the derivative of your something. And if you set that equal to 0, you essentially end up solving that equal to 0. So either way, you're finding where the derivative is equal to 0. And we don't worry about this equaling 0 because the distance can't equal 0 because the distance between these 2 points isn't 0. They're not the same point. Okay, so anyway, lots of words to say that we can just minimize this. So I'm going to take the derivative of that. Oh, no, I'm not. I'm going to take the partial derivatives of that. Apologies. So let's call this f just to make it a little nicer. So I'm going to find fx, and that's going to be 2 times x minus 2 plus 2 times x plus y. And set that equal to 0. And also I'm going to find, yeah, sure, fy, and that's going to be 2 times y minus 1 plus 2 times x plus y equal to 0. Excuse me. So we should probably just multiply these out. So I have 2x minus 4 plus 2x plus 2y equal to 0. And this one's going to become 2y minus 2 plus 2x plus 2y equal to 0. All right. So let's see. We've got a 4x plus 2y minus 4 equal to 0. Solving for y, we've got, sure, y equal to 2 minus 2x. Over here, let's solve for y also. I've got 4y equal to 2 minus 2x. And then I can just plug that in over there and say 4 times 2 minus 2x equals 2 minus 2x. I think we're going to get x equal to 1. Yeah. Now, it's not super important how I saw that, but I saw that 4 times a thing was equal to the same thing. The only kind of thing when you multiply it by itself and it doesn't change is 0. So I was like, oh, this thing has to be 0, which means x has to be 1. Or we could do the math, right? I mean, the thing we don't want to do is divide both sides by 2 minus 2x. That'd be a big problem. So we have 8 minus 8x equals 2 minus 2x. Add 8x, subtract 2. Oh yeah, x equals 1. And then y is going to be 2 minus 2. So y is going to be 2 minus 2, which is 0. And then we should check. It's not too bad. It just always feels like it takes so long. So I will say, definitely on your exam, don't do more work than you need to. If you don't actually have to check to show it's a minimum, don't. You probably, I would imagine, knowing Dr. Liddell, he would probably want you to, but make sure that you actually have to do the thing before you start doing it. So let's see, our second partial with respect to x here is going to be, I should have multiplied this out. Let's see, it's going to be 2 plus 2, which is 4. Our second partial with respect to y is going to be 2 plus 2, which is 4. And our fxy is going to be 2. 1 2s. So then, oh no, we're good. I was worried for a second. I was looking at this thinking we were going to get 0 for d, which is going to be a problem, but we're not. We're going to get 14. 12, sorry, 12. Which is positive, which means then since the second partial is also positive, we have a minimum. So we have a minimum at the point or minimum distance at the point x equals 1, y equals 0, and we should go back and find the z value, right? Because we actually do need to find that to answer the question. So z equal to, let's see, z equal to x plus y minus 1. So z equal to 1 plus 0 minus 1, which is 0. So we can say that the point 1, 0, 0 on the plane x plus y minus z equals 1 is the point closest to 1 negative 1. And then if they ask you to find the distance between them, you can just find the distance between them. Right. What else? What other topics? Well, I have ideas if you don't. Okay. I feel like we should do a couple limit problems. So let's do some of the, I feel like I had some examples over here too. I do, but we'll kind of, so looking at his examples, here's an easy one. The limit as x, y approaches 5 negative 1 of x to the 4th plus 4x cubed minus 5xy squared. And I say easy one because there aren't any problems with this function, right? There's no worry about dividing by 0. We can literally just substitute in the x and the y values and we're done. It's going to be 5 to the 4th plus 4 times 5. Is that an x? It is an x. 4 times 5 cubed minus 5 times negative 1 squared. So that's going to be 5 to the 4th. 5 to the 4th is 625. And then 5 cubed is 125 times 4 is 500 minus 25. So we end up with 1100. I feel like kind of big numbers for not having it, but I mean, they're not unreasonable, I suppose. Okay, let's look at this next one. The limit as x, y approaches 0, 0 of x squared over x squared plus y squared. Now, typically, when you see something that is a 0 over 0 type, what you should start doing at first is trying a couple paths. I would almost always recommend letting one of your paths be either x equals 0 or y equals 0. It's usually going to result in something nice. In fact, this one I think it might totally do. I think usually they give you the same result, but I think here they're actually going to give us different results, which will be done because we'll have non-existing. So if we try x equal to 0, we're going to have the limit as y approaches 0, right? Because x is already 0, of 0 over 0 plus y squared. And then the limit as y approaches 0, what's 0 divided by 0 plus y squared? Well, no, so this is where we have to be very careful. 0 divided by y squared, ignoring the fact that y is getting close to 0, right? We're just like, y is a number. In fact, it's actually not 0, right? The limit as y approaches 0 means y is getting really, really, really close to 0, but actually doesn't ever get to equal 0. So the whole point of this idea here is that this expression is very, very specifically 0 divided by not 0. And 0 divided by not 0 is what? Right. And now, what's the limit as y approaches 0 of a constant? just that constant. So the whole idea with this path typically is the whole thing just becomes 0 before you even take the limit. And then when you take the limit, you just get 0. But I think we're actually gonna do something different if we let y equal 0. If we let y equal 0, we're gonna have the limit as well. We're done with y, so we're just gonna talk about x getting close to 0 now. And if y is 0, we're gonna have x squared over x squared, which again is a 0 over 0 type. But what's x squared divided by x squared? Right. So this becomes the limit as x approaches 0 of just 1, and then that's just 1. And then, since these are different, the limit doesn't exist. So if you can find two different paths where the limits are different values, the limit doesn't exist. And again, the paths have to go through the origin or whatever you're approaching, right? Most of the time it's through the origin. And let's look at one that's a little more, I feel like this is a little atypical because usually both those paths result in the same sort of answer. Let's look at the next one, which is the limit as x, y approaches 0, 0 of 8x squared y squared over x to the 4th plus y to the 4th. And again, I would recommend trying one of the paths to be either x equal to 0 or y equal to 0. If we do y equal to 0, we're going to get the limit as x approaches 0. And I'm not writing the y because I know that what y already is. So y isn't approaching something. We know that y is 0. And then I'm just going to get 8 times x squared times 0 over x to the 4th plus 0. So now I'm going to ask you the same question I just asked you a minute ago. What's this expression equal to before I take the limit? Right. So then I just have, and now I would probably encourage you to write this step and then say it's equal to 0, although it would be perfectly correct to say it was just equal to 0. So now I will point out as well, if we choose the other 0 path, if we choose x equal to 0, we're going to get the same thing. You're going to get 0 on top, you're going to get y to the 4th on the bottom, and then the limit's going to be 0. So we have to try something else. So what's another path that goes to the origin that might seem reasonable to choose here? Okay, so some common choices are y equals x, or y equals x squared, or x equals y squared. Usually I try to avoid roots, but roots are okay, but especially odd roots, so like you can do y equals the cube root of x. Often the choice I'm going to try to make is going to be so that essentially the powers on top and the bottom end be kind of the same. So in this case, y equals x is a really good choice, which definitely goes to the origin. So if we do the limit there, it's going to be the limit as I'm going to replace the x's with y's. Sorry, the y's with x's. I like to keep the x's if I can, but it doesn't really matter. So I know that x is approaching 0, and I have 8 times x squared over x to the 4th plus x to the 4th. And look at what happens. I have the limit as x goes to 0 of 8x to the 4th over 2x to the 4th. X to the 4th cancel. So we get the limit as x approaches 0 of just 4. And that limit is 4. And again, the overall limit doesn't exist because these are different. So the limit does not exist. Okay. Let's see here. Yeah, let's look at one more because, well, I mean, we can look at as many more as you want, but there's one more I think we should look at. Let me actually, I do have the solution. So let me check one thing before I do this one just to see. I want to pick one that exists. Oh, that's interesting. All right, that's a cool way of doing that. Okay, sure. Oh, wow. That's really interesting. I would never have thought of doing it that way, but it totally works. Okay, I'm going to show you the way he did it because, like, I think it's nicer than what I would do. So let's say we want to look at E here. The limit as x, yes, of course, as xy goes to 0, 0 of xy squared over the square root of x squared plus y to the 4th. double check them. He has a different problem written here in his. Okay, we can still do it. That's fine. We'll do this problem. So he has a slightly different problem written in his solutions. It's okay. So the way to tackle a problem like this, or one way to tackle a problem like this, which seems, I gotta admit, I never would have thought of this, but you can divide the top and bottom by xy squared. Now it might not always work, but so I guess I should back up a little bit. The kind of intuition here is we would still try different paths, but what's going to happen is all the paths are going to give us 0. Now, that doesn't mean the limit necessarily is 0. It just means we haven't found the path where it wasn't, but it could be 0. So if you've done a couple of things and you get 0, you're like, oh, maybe it's 0. So one thing to try is to divide the top and bottom by xy squared, which doesn't seem particularly intuitive to me, but let's see what happens. So the limit is xy goes to 0, 0 of xy squared over xy squared. Well, that's going to be 1 over, I'm going to write this. I'm going to write 1 over xy squared times the square root of x squared plus y to the 4th. Okay, so that's going to be the limit as xy goes to 0, 0. The top's 1. And now here's what I'm going to do. I'm going to bring this xy squared into the square root, but I have to square it when I do that. So I'm going to rewrite this as the square root of 1 over x squared y to the 4th, right? I'm squaring that thing, times x squared plus y to the 4th. And now I'm going to distribute it. So I have the limit as xy goes to 0, 0 of 1 over the square root of, let's see. So 1 over x squared y to the 4th times x squared is going to give me 1 over y to the 4th. And 1 over x squared y to the 4th times y to the 4th is going to give me 1 over x squared. And now we have to ask ourselves what's happening here. Well, as x and y both get really, really small, closer and closer to 0, what's going to happen to 1 over y to the 4th? It's actually going to get bigger, right? Because we're dividing by a small number, so it's getting really, really large. So this is going to go to infinity. And it's definitely going to be positive infinity because it's to an even power. And in a similar way, 1 over x squared is also going to get really, really large. Well, now I've got 1 over infinity, which is going to 0. I would never have thought of doing it that way, but it is valid. It's kind of neat. It's definitely, there are other ways of doing this, or kind of do like a squeeze theorem kind of thing, but I feel like this is actually maybe better. I will point out, so let's actually, I feel like you could ask a question like this. So let's look at one more. Let's look at something like the following. Let's say we had the limit as xy goes to 0, 0. Let me think about what makes this. Okay, I want to do that. Sure. So let's say we had x cubed y squared over the square root of x squared plus y squared. Okay, so the last one was relatively easy, that things kind of matched up in that the power of y here was twice the power of y there, the power of x here was twice the power of x there. We really, when we do this sort of method where we do this thing, we want to pay attention to the things in the denominator. So even though I've got x cubed y squared, I actually don't want to divide top and bottom by x cubed y squared. I want to divide by xy, powers that are half of those powers. So this was an x to the 4th, y to the 4th. I want to divide by x squared, y squared. So let's see what happens when we do that. I'm going to get x cubed y squared over xy, and I'm going to get 1 over xy times the square root of x squared plus y squared. In the numerator, I'm going to have x squared y, and the denominator, bringing that thing in, I'm going to get the square root of x squared over x squared y squared plus y squared over x squared y squared. Basically, you want to make the choice so that when you bring that in, the numerators cancel. So that this now is equal to the limit as xy goes to 0, 0 of x squared y over the square root of 1 over y squared plus 1 over x squared. Now I'm going to ask you the same thing I asked you before. What's happening to 1 over y squared as y is getting really small? Right. So this whole denominator is getting larger and larger and larger. So this is going to infinity on the bottom. And as xy goes to 0, 0, where's x squared y going to? Right. So 0 divided by infinity is definitely 0. So that's how you can tackle